Okay, let's tackle the subject of gravitation. You can see in the word gravitation the word gravity. It's very related to the concepts you've already learned, like weight, okay, gravity. We've kind of used those interchangeably. Gravitation, of course, is related, but it suggests a wider reality, okay, a bigger reality. And so what I want to do is set up for you our current understanding of weight and expand it to see just how far-reaching it is. Let's go. Okay, on the screen you see a picture of the Earth, and that person there on top of the Earth is supposed to be you, obviously not to scale. Okay, now we know something about the value of the force between the Earth and you. Okay, that is the force of weight. We know how to calculate the force of weight, right? And that's just using Newton's second law, mg. Okay, so we know that the force between you and the Earth is your mass times 9.8. Okay? Now, let's zoom out a little bit and look at what else is near the Earth. Okay? We have right here the moon. Okay? The moon. And in the 1600s, Sir Isaac Newton was trying to think about what is it that makes the moon go around the Earth. Okay? For a long time, for literally thousands of years, astronomers had a very different understanding of what makes the sun and the moon, the planets and the stars move. Okay, and here was Newton's stunning insight. Okay, you take it for granted today, but this was a huge insight, 350 years ago. This is his insight. He realized that the same force that makes the apple fall, okay, when you drop an apple, the same force that makes the apple fall makes the moon go around the Earth. Gravity, right? In other words, there is a force, okay, between not just you and the Earth, right? But also between the moon and the Earth. Okay? And here's the thing that's so big about that. If you realize that there's a force between the moon and the Earth, there's a force between you and the moon, right? There's a force between the Earth and the sun way over there. And there's a force between you and the sun, and the moon and the sun. And all of a sudden we realize that every object of mass in the universe pulls on every other object of mass in the universe. Okay? Fortunately, Newton didn't leave us there, okay, just with this idea, but he was actually able to put his idea in equation form. Okay? And this is the equation that he came up with, and this is what is called Newton's universal law of gravitation, because it applies not just to between trying to calculate your weight on Earth, but between the pull between any two objects. Okay? And here's the formula. All right? So for any two given masses, right, you and the Earth, okay, the sun and the moon and the Earth, you take those two masses, m1, m2, you multiply their masses together in kilograms. Okay? You take the distance between their centers, okay, between the center of the Earth and the center of the moon, for example, and that's what this is, okay, center to center distance. And you then multiply it by this crazy thing here. This is called the universal gravitational constant, okay? It's a value like 9.8, except it's constant all over the universe. Okay, very remarkable universal gravitational constant. It's the same everywhere in the universe, unlike 9.8, right? 9.8 is only true on Earth. And it has a crazy value, okay? It's not a number you'll have to memorize. It's an incredibly small number, okay? That's 1/100 billion. And it's also got crazy units. It just makes all the units work out so that this will be in newtons. Okay, let's see if we can use this formula, okay, make it do some things for us. All right, let's go to the next screen. Okay, you see an example here. I just picked two masses. This could be like Jupiter, M2, right, and then one of the moons of Jupiter, M1, or the Earth and the moon. All right, it could just be two objects on Earth, like a steel ball and an iron ball, for example. All right, and we can calculate the force between these two objects. Now, before we do actual forces, I want to show you that we can also do the proportional reasoning, right? In other words, we can say, what happens if, for example, I double this one's mass, right? What's going to happen to the force between them? Or what happens if I triple the distance, right? Let's say M1 is doubled, okay, and the distance is tripled, like that, okay? Let's see what happens proportionally to the force. So the new force, right, F new, would be 2m1 here, and then underneath, right, we get the 3D quantity squared, and you're going to see that this works out to 9, okay, or 2/9, right, 2/9 the original. 2/9 the original, which is that. Okay, so this is an example of proportional reasoning at work. In other words, when we made these changes, right, we tripled the distance but doubled one of the masses, okay, it ended up being that the new force was only 2/9 as much as the original. Okay, so what you want to notice here is that increasing the masses, right, increases the force, okay, but increasing the distance decreases the force, right? We say that these are directly proportional, okay, that's the symbol for proportional. And we say that the distance between the centers, okay, notice I use the centers here, okay, that, actually, let's write it this way, the force is proportional to the inverse square, okay, we say the inverse square of the distance between the two masses. All right, we're going to do one more problem here with this new universal law of gravitation. We're actually going to plug some numbers in, okay, and you've done this a lot in physics. There is something that's additionally challenging about this formula. Besides it being a little more complicated, the real challenge here for students is the big numbers that are often involved. Okay, so I'm going to use some numbers that you might see, okay, when we're talking about forces between planetary objects. All right, let's go to the next screen. Okay, we're going to use the same example, except now we're going to make M1 be the Earth. Okay, and M2 is going to be the Sun. All right. Now, watch what happens here. Okay, as you realize, these are extremely massive objects. Okay, the mass of the Earth is 5.98 times 10 to the 24th kilograms. I mean, we hardly have prefixes for a number that big, right? The Sun is even bigger. It's about 1,000,000 times bigger than that. Okay. And then even the distance between the two is huge when it comes to meters, right? You're going to have to express this distance in meters. I don't remember it exactly, but it's something times 10 to the 11th. Let's just say 3 times 10 to the 11th. Okay? Now, look at all these exponents that are going to come together when you try to calculate this force. So you're going to have to make sure that you're comfortable with using the EE button, okay? And we'll go over this a little bit in class. But you really need to be comfortable with exponents because there's going to be a lot of exponents coming together on your calculator. Watch how this looks like here. Okay, first comes G, that's 6.67. And watch how I write. I'm going to write the abbreviated form of the exponent. Okay, so instead of writing times 10 to the negative 11, I'm going to write E negative 11. Right, it saves me a little bit of writing. You can do the same. So that's G. Now comes the first mass, right, the mass of the Earth. And then the mass of the Sun, which I made a mistake here earlier. It's 10 to the 30th, not 10 to the 3rd. Okay, and all of this gets divided by another monstrous number, which we said was roughly the distance between the Earth and the Sun. But look what happens here. The whole thing gets squared. All right. So I'm going to let you do that on the calculator on your own, and when you come to class next time, we'll see if you got it right or not. Okay? That concludes our lesson on gravitation, and we'll see you in class next time.